Archival footage of a ship in heavy seas, then cut to calm blue water with a massive wake. Slow zoom on an old landing craft struggling toward a beach. Overlay text, 21 knots, 40,000 tons, thousands of Marines. Imagine trying to land an entire mechanized infantry battalion on a hostile shore under fire with no friendly port in sight. For decades, that problem broke navies. The physics is brutal. You need to move thousands of tons of men, vehicles, fuel, and ammunition across open ocean at speed, then transition instantly from blue water to beachhead. One wrong compromise in hull design, propulsion, or aviation integration, and your force arrives too slow, too vulnerable, or without the air cover it needs to survive. Today, the USS Bataan LHD-5 and her sister Wasp-class ships solve that exact impossible equation. And right now, with tensions high in the Middle East, she's part of the force carrying roughly 3,000 Marines and sailors toward the Strait of Hormuz. Map of the Strait of Hormuz with oil tanker routes animated. Global oil flow percentages overlay. Cut to historical photos of amphibious landings, Normandy, Incheon modern MU exercises. The driver is simple but unforgiving. 20% of the world's seaborne oil passes through a narrow 21-mile wide choke point. Any disruption costs billions per day. When a crisis demands rapid response without relying on fixed air bases or friendly ports, the U.S. Navy and Marine Corps use an Amphibious Ready Group, ARG, centered on a big-deck amphibious assault ship like Bataan. A typical Marine Expeditionary Unit, MEU, of 200, 500 Marines is self-contained. Infantry, artillery, logistics, and aviation combat element. The ship must carry them 9,500 nautical miles at sustained speed, then launch them 20 to 50 miles inland using helicopters, tiltrotors, and hovercraft, all while defending itself. Simple animation of displacement hull versus planing hull. Equation overlay. Power required is proportional to velocity superscript 3 for displacement ships. Graph of wave-making resistance peaking at hull speed. Cut to CFD simulation of bow wave and wake. Start with first principles. Any ship displacing 40,500 tons at full load has to push an enormous volume of water out of the way. Hull speed, the theoretical maximum efficient speed, is roughly 1.34 times square root waterline length in feet. For Bataan's 844-foot hull, that's around 23 to 24 knots. Push harder and wave-making resistance explodes because you're climbing your own bow wave. The power required scales with the cube of velocity. Bataan's two boilers feeding geared steam turbines deliver 70,000 shaft horsepower to two massive propellers. That's enough to reach 23-plus knots, but every extra knot costs disproportionately more fuel. Now layer on the real problem. You also need an 80,000-plus square-foot flight deck for simultaneous helicopter and V/STOL jet operations, a 266 by 50-foot well deck for LCAC hovercraft, vehicle storage for hundreds of tons of equipment, and berthing for over 3,000 people. Add stability. The ship must resist rolling in Sea State 5 while launching aircraft. Too narrow and it rolls badly. Too wide and it becomes a slug in the water. The Wasp-class hull form is a carefully tuned compromise, length-to-beam ratio optimized for both speed and aviation deck real estate. Exploded 3D model of USS Bataan, showing layered decks. Cutaways. Well, deck flooding sequence with LCAC launching. Flight deck with MV. 22 Osprey tiltrotor conversion. F-35B short takeoff roll. Animation of steam turbine cycle. Hangar elevator operation. Engineers solve the integration puzzle with a multi-mission, sea-based design. Propulsion and endurance. 2 fossil fuel steam plants. Later ships switch to gas turbines plus auxiliary electric motors for better low-speed efficiency. Range is engineered around the cube law. Cruise at 20 knots to conserve fuel for weeks of operations. Well deck and surface connectors. The flooded well deck launches 3 LCAC hovercraft. Each LCAC uses high-power fans to create an air cushion, reducing friction to near zero. This lets 60-plus ton payloads cross from ship to shore at 40-plus knots over water, reefs, or even soft sand, bypassing traditional surf zone problems that destroyed landing craft in World War II. Aviation integration. The real magic: 9 helicopter spots on a through deck. 2 massive elevators, 70,000-pound capacity each, move aircraft between hangar and flight deck in minutes. The ship routinely operates MV-22 Ospreys. Tilt-rotor efficiency gives 3 times the range and speed of legacy helicopters. CH-53E/K heavy-lift Helos, H-1Z attack helicopters, and up to 20-plus F-35BS in Lightning carrier configuration. Why does this matter? Traditional helicopters are limited by rotor aerodynamics, induced drag, and retreating blade stall cap their forward speed. The Osprey's prop rotors tilt forward after takeoff, turning it into a turboprop airplane. That single clever mechanical solution, despite its own weight and complexity trade-offs, shatters the 150-knot barrier for vertical lift aircraft. Command and logistics layer. The ship carries hospitals with 6 operating rooms and 64 beds, desalination plants producing hundreds of thousands of gallons of fresh water daily, and massive JP-5 fuel storage for aircraft. Everything is designed so the MEU can fight for days without shore resupply. Side-by-side comparison table. Traditional LHA versus Wasp-class capabilities. Graph of aircraft sortie rates. Graphs. Fuel consumption versus speed curve. Weight versus payload trade-off. Cost overlay. $2. $3 billion per ship in today's dollars. Animation of radar cross-section limitations versus true supercarrier. Nothing is free. Steam or gas turbine. Plants are thermodynamically limited. Carnot efficiency means a lot of heat goes out the stack. Modern electric drive concepts promise better part load efficiency, but add weight and complexity. The flight deck is shorter than a supercarrier, so F-35BS use style, short takeoff/vertical landing. They carry less fuel and ordnance than catapult launch jets. Carrying both a full well deck and a big aviation facility forces design compromises in internal volume. Every marine vehicle stored below displaces potential aviation fuel or ammunition. Vulnerability. A 40,000-ton ship is a big target. Defensive systems, Sea Sparrow, Ram, Phalanx, exists, but the ship relies on escorts and its own aircraft for layer defense. The popular misconception that these are mini-carriers is only half true. They are hybrid sea control and power projection platforms, excellent at what they do, but deliberately not optimized for sustained high-intensity air warfare, like a Nimitz or Ford-class. Maps showing current deployment context, without speculation. Cost breakdown animation. Long shot of Bataan at sea with aircraft cycling. Is this technology viable for future? Absolutely. The Wasp-class and follow-on America-class designs have proven they can deliver credible combat power thousands of miles from home with minimal shore infrastructure. They turn physics constraints into operational flexibility. But the economic reality is stark. Each ship costs billions to build and tens of millions per year to operate. The U.S. maintains a fleet of these precisely because the alternative, relying solely on land bases or pure carrier strike groups, leaves dangerous gaps in rapid crisis response. Slow motion of LCAC launching, Osprey lifting off, ship cutting through waves, fade engineering blueprint morphing into ocean horizon. Nature doesn't care about geopolitics. Water resists motion with the cube of speed. Air limits rotorcraft performance through induced drag and stall. Yet human ingenuity keeps finding ways to thread those physical needles, building floating cities that can cross oceans and then strike inland within hours. The USS Bataan doesn't shock anyone through hype. It works because engineers respected the laws of physics, accepted painful trade-offs, and optimized for the one mission that matters most: getting the right force to the right place before the window closes. Subscribe/sources/ what engineering challenge should we break down next?